Hello everybody and welcome to section 3.11, which is going to be talking about hyperbolic functions. And I want to start off with, double check the problems on the syllabus. I kind of just chose the ones that I think are the only ones you really need to focus on. Fair warning, this section is just going to be a lot of, just writing down formulas, a lot of, this is the function and how it's defined, this is its derivative, this is how we define the inverse hyperbolic function, this is how we define its derivative. So it's just going to be a lot of, writing out basically identities and things like that. So keep that in mind. But I just want to get it all out there for you. That way you guys can have it in one condensed format, both in the book and in the lecture. We'll do a couple problems, of course, just to use them. But for the most part, it's just a lot of writing. And I want to say right off the bat, I've got my own written out, just because, if I'm halfway through the lecture, it keeps me on track. But also because there are some of these formulas that, I used once, and I mean literally once in my entire mathematical career. So is it just memorized because I'm ready and I'm going to be able to use it at any given moment? No, I used it once and I've never used it again since. So as far as the functions go, don't memorize these, especially in such a format like this, condensed 6 weeks, online, everything's moving so fast. Don't focus on making flashcards and memorizing these. I don't want rote memorization. I want you to be able to use the formulas. That said, later down the road in Calc 2, you're going to be expected to know them, but I know some Calc 2 teachers that give you like a formula sheet, so or in the question, they kind of bake it into the question. Knowing that inverse sine hyperbolic is defined as, find the following. So again, don't waste time all weekend just trying to memorize these formulas. I just want to make sure that you guys know how to use them, essentially. Okay, so that said, here we go. A lot of writing. We're going to first define the hyperbolic functions. Starting with sine hyperbolic. And this is how we write it out. Sine hyperbolic of x. It is defined to be e to the x minus e to the negative x over 2. Now, the way we say it is sine hyperbolic. And it's written S-I-N-H to denote that it's the hyperbolic version of the function. All right, and this will go for all the rest as well. Cosine hyperbolic, right, looks like cosh, but it's cosine hyperbolic, e to the x plus e to the negative x over 2. Notice how these hyperbolic functions are actually defined by the exponential function, which is pretty neat. And before we even touch on tangent, because it is really just still the ratio, I want to take a look at just a real quick sketch of a graph for the function, or at least for these two, because the graphs of these two are something you should know, in my opinion. Right, because you will encounter these functions again. Typically, 9 times out of 10, it's one of these two functions, sine hyperbolic or tangent hyperbolic, just based on the way they're defined. So what you can do is actually graph y equals e to the x, and you can actually graph there we go. I'm not going to draw you the most perfect graphs, but sine hyperbolic sort of hugs these two graphs pretty nicely. Just to give you like a sort of a general shape of the graph. And then for cosine hyperbolic, again, it's very reminiscent of trying to graph like y equals e to the x, and then y equals e to the negative x. And it should give you some sort of shape again, sort of close to this. And then cosine hyperbolic, I guess maybe I should, yeah, a little bit of overlap here. Let me cut back on that. There we go. Oh, sorry, I didn't mean to put the inverse notation on sine hyperbolic. Really jumping the gun there. But these are just basic shapes of the graphs. Sine hyperbolic just kind of comes in and does this smooth little wiggle. It almost looks like y equals x cubed if I were to reference a function that looks like that. And then cosine hyperbolic kind of comes in and hangs and then goes back up. And they're useful in different situations in the real world. I know for a fact, we look at these cosine hyperbolic functions. Imagine holding up like a piece of string or a chain. It doesn't form a perfect hyperbolic, like y equals x squared sort of pattern. It sort of depends on how taut you hold it, how much slack it gives. The way we define those curves is based on the cosine hyperbolic function. Or if you think about the St. Louis arch, right? Think about if you ever been to St. Louis and saw that arch, which is quite a landmark to see. That arch has that upside down cosine hyperbolic shape, which is kind of neat. So basic sine hyperbolic and cosine hyperbolic, and yes, tangent hyperbolic is simply just defined as the ratio of those two, which means you can write this up top, write this on bottom, and simplify if you need to, and then have it be a ratio of exponential functions if necessary. But we're not even going to go there. We're just going to write it out as a ratio. And then same thing with the other reciprocal functions. We can reciprocate all this, like flip numerator, denominator, and get all the other ones to pop up for free. So cosecant hyperbolic of x is 1 over sine hyperbolic of x. Secant hyperbolic of x is 1 over cosine hyperbolic of x. Cotangent hyperbolic of x is cosine hyperbolic of x over sine hyperbolic of x. Like I said, I'm not going to graph every single one of them and get into it. Your calculator actually has these. If you have like a TI-83 or a TI-84, your calculator actually has them stored, but usually what you have to do is on your calculator hit the second button and then go down here to catalog, and you can scroll through the list of all the extra features that the calculator has, and they're in alphabetical order, and you can go hunt these down. I believe it only has these 3. Maybe the newer software has all 6, but I think it has either these 2 or these 3 for sure if it's like a TI-83, 84. If it has the newest software, these might actually be in there as well. I haven't actually checked. Again, never really had a need to use them. So those are our hyperbolic functions. When you think about trig functions, if you had me for trig, you'd hear me say these functions are circular functions, right? They just travel around the unit circle. Algebra, it's all about x and y, Cartesian coordinates. When you get into trig, it's a whole different class of functions. They're periodic functions, right? Circular functions. They repeat, they repeat, they repeat, they repeat. These are hyperbolic functions, right? So they more so follow the pattern of a hyperbola. So just different class of functions. But you can see that it sort of is very similar to how the trig functions are, except they're not defined, on the unit circle. We define them with the exponential function. So I'm not going to give you too many, but here are some hyperbolic identities. And again, if you think back to trig, you're thinking, oh my gosh, I had so many identities, double angle identities, half angle identities, sum to product formulas, product to sum formulas, all that good stuff, power reducing formulas. I'm not going to give you that much. I'm just going to give you a short list, just so you can bounce back and forth between a few. Let me write. first things first, sine hyperbolic of negative x is negative sine hyperbolic of x. And this should key you in to say, wait a minute, I know a class of functions that behave like that. Odd functions behave like that. So this function is an odd function, and it has that origin symmetry from when you look at the graph that I gave you. Cosine hyperbolic of negative x is cosine hyperbolic of x. And again, we had a specific class of functions like that. Those were our even functions. And again, this should be familiar because sine of x, our original sine x was an odd function. Our original cosine x was an even function. But now it's just triggering your brain to remember it even better. Cosine hyperbolic squared of x minus sine hyperbolic squared of x is equal to 1. Okay, this one's a little bit different because we had in trig, cosine squared of x plus sine squared of x was 1. For the hyperbolic functions, it's actually different. Cosine hyperbolic squared minus sine hyperbolic squared is 1. Right, so it tweaks that identity a little bit different. And that's just based on the way they were defined. We also had back in trig that 1 minus tangent squared of x. We had back in trig that 1 plus tangent squared of x was secant squared of x, but these are hyperbolic, so it's a little different. 1 minus tangent hyperbolic squared of x is secant hyperbolic squared of x. And again, you can see that h is very notation. Without the h, it's a completely different function. So we have to be careful. So here is if we have sine hyperbolic of two angles x and y, then we can break it up and have sine hyperbolic x cosine hyperbolic y plus cosine hyperbolic x sine hyperbolic y. This should be familiar to your old sine a plus b is sine of a cosine b plus cosine a plus r times sine of b. So it's basically the same formula, just with hyperbolics. Cosine hyperbolic of x plus y is cosine hyperbolic of x cosine hyperbolic of y. And again, if you remember your trig well, cosine a plus b should be a minus. The plus should be a minus, or the minus should be a plus, but this does not change sign. So it is a little different here. So again, go back and check your formulas for cosine a plus b. You would see cosine a cosine b minus sine a sine b. But this is dealing with a different set of functions here. We're talking about hyperbolic functions. So the identities behave a little bit differently. We saw that, of course, here was a big glaring difference from our original Pythagorean identity. And that's it. That's enough to, get you started studying hyperbolic functions and get you through, any homework questions. They may ask you like, hey, prove this is something, they'll give you like an identity. And the trick is to just write it out like this and then see what cancels. They'll probably give you some angles here so that you can look at them pretty quickly, like sine hyperbolic of 0. Oh, okay, well that's just 0, so I would just cross it out, right? Things like that. So again, not going to overwhelm you with any more identities. You will get more functions, like we need to look at derivatives and stuff like that. But you'll notice just how wacky things get here in a second. So again, we looked at hyperbolic functions. We looked at a couple identities. Now let's write down the derivatives of those hyperbolic functions. Again, this whole section, 3.11, I'm not asking you to make a stack of flashcards this big and study those. No, I want you guys practicing other problems to get the big picture. Again, these are more just jot them down. You're going to need to reference them. If it's ever a situation where I think you necessarily need one of these, I will provide it for you. I think that's fair, especially at this pace. But again, when you get into Calc 2 or Calc 3, no promises. I do know some teachers that give you these. I do know some teachers that say, no, everything is either in your brain or it's not. So it just kind of depends who you subscribe to there. So if y is equal to sine hyperbolic of x, then y prime is cosine hyperbolic of x. Shouldn't feel too strange, right? When we differentiate the trigonometric sine function, we get the trigonometric cosine function. Now that we're dealing with a hyperbolic sine function, when we differentiate it, we still get a hyperbolic cosine function. If y is cosine hyperbolic of x, then, and here's one of those situations where it does feel a little different. The derivative y prime is sine hyperbolic of x. Remember when we differentiated the trig function cosine of x, we got y prime to be negative sine of x. Here, there's no negative that kicks in, right? It just goes sine hyperbolic to cosine hyperbolic. I differentiate cosine hyperbolic, I get sine hyperbolic. I differentiate sine hyperbolic, I get back to cosine hyperbolic. They literally just flip-flop back and forth between each other, and they never change sign at all. With the trig functions, they did change sign, and we had to watch out for that. So little differences, just slight little differences here and there. If y is tangent hyperbolic of x, then y prime is secant hyperbolic squared of x. Again, feels familiar. And let's look at their reciprocal functions. If y is cosecant hyperbolic of x, then y prime is negative cosecant hyperbolic x, cotangent hyperbolic x. Up next is secant hyperbolic of x. Y prime is negative secant hyperbolic x, tangent hyperbolic x. And if y is cotangent hyperbolic x, then y prime is negative cosecant hyperbolic squared of x. So again, based on our old trig functions derivatives, these patterns mostly look the same. Maybe we're just off by like a negative sign here or there. We just want to be a little careful about making sure we get the proper sign on our derivative. So we've got that. So we've got that taken care of. Again, really not much difference here. Just watch that extra little negative that we get with trig functions that we don't get here when we differentiate between cosine hyperbolic and sine hyperbolic. Watch that difference where the negative just never pops up for us. But the patterns are all still the same. Right? It looks like we're almost dealing with the same functions. They just have an h in them. Well, they're completely different functions. They have totally different graphs. So that h is there for a very, very important reason, to give us an entirely different class of functions. Okay, like I said, a lot of writing formulas. I do feel like the book just kind of crams this in right here at the end of chapter 3 because they've probably had, as they've gone through several editions, I think we're on the 8th edition now, as they've gone through several editions, I think they've just decided we don't know where else to put it, so we're just going to put it here. And they just kind of cram all this stuff in at the end of chapter 3. So it might look overwhelming because you're doing a lot of writing, and it feels like you might have to do a lot of memorizing. Don't worry, don't freak out about it. So next we want to look at inverse hyperbolic trig functions. Let's get those down and out of the way. sine hyperbolic inverse is written as the log of x plus 1 plus x squared, or x squared plus 1, some people remember. And x could be any real number. Right? Cosine hyperbolic inverse of x is going to be given by the natural log of x plus the square root of x squared minus 1. And for here, x is going to have to be larger than 1. I'm going to say it could also equal 1. Yeah. Why leave that out, right? If x is 1, we would be doing the log of 1. That's 0. So we'd get 0. We'd still get a result. So I should keep that 1 in there. Right? No reason to drop it out if it absolutely can be there. But we don't want to take the square root of some sort of like negative number. So we don't want to deal with fractions in there. And of course, we don't want to take the log of a negative number with some crazy complex stuff. So of course, we'll just keep things greater than or equal to 1. So there's a little stipulation there. And it should be clear that the log function will pop up with the inverses because the sine hyperbolic function is defined using the exponential function. Cosine hyperbolic is defined using the exponential function. So it's natural that the inverse would be the log function. Natural log is the inverse of an exponential function. So it sort of just makes good sense. Tangent inverse hyperbolic, or tangent hyperbolic inverse of x is 1/2 log, here's a weird one, 1 plus x over 1 minus x. A very, very strict domain there. We got to be between, not between 1 and 1, between negative 1 and positive 1. It's a really, really, really weird function there. And I'm not even going to give you the reciprocal ones because really you can just do 1 over, 1 over, 1 over. There's no point in rewriting all that just so I can rewrite 1 over all that stuff with the log business. All right, so if someone were to hand me like a cosecant hyperbolic inverse, I would just look at the reciprocal 1 over sine hyperbolic inverse and do my work that way. Plus, it will be so rare that you actually get to use these functions. So, again, like I said, they're really crammed into the back of that chapter 3. So I got to keep track of everything I have covered. I've done it. You got that listed. Again, I told you guys it's going to feel like just a big whole list of things that you need to know. I'll do a couple problems, so don't worry about it. But one more thing, because we have not talked about derivatives of inverse hyperbolic functions. So we haven't talked about the inverse hyperbolic functions, or the derivatives of inverse hyperbolic functions. Let's make sure we've got. Okay. So if y is sine hyperbolic inverse of x. Now again, we're dealing with hyperbolic functions, not the inverse hyperbolic functions, not just the hyperbolic functions. Then y prime is 1 over the square root of 1 plus x squared. If y is cosine hyperbolic inverse, then y prime is going to be, let me make sure I get this all fit in here, 1 over radical x squared minus 1. Make that look a little nicer. myself some more space here. If y is tangent hyperbolic inverse of x, then y prime is 1 over 1 minus x squared. If y is cosecant hyperbolic inverse of x, then y prime is, this one's a little weird, there's actually going to be a negative 1 over absolute value of x, square root x squared plus 1. I can tell you that I probably have never used that. If anything, worst case scenario, I may have used it once somewhere ever, and I probably looked it up again. If y is secant hyperbolic inverse, we're going to lose that absolute value, though, I know that much. Y prime is negative 1 over x times the square root of, I believe it's x squared, 1 minus x squared. I was going to say x squared minus 1, and I would have been incorrect. And then cotangent hyperbolic, and we're all set. So if our function y is cotangent hyperbolic inverse, we'll go for y prime is negative 1 over 1 minus x squared. Nope, sorry, I take that back. No negative. Yeah, these are the same. So these two, be careful, they are actually indeed supposed to be the same. I believe that completes my entire list of stuff. And it does. Good. So again, a little weird. But, you know, if you looked at the inverse trig functions, like instead of the hyperbolic, if you just looked at tangent inverse of x, and you differentiated it, you got 1 over 1 plus x squared, right? So, again, these exhibit sort of the same patterns, but based on the way they're defined from the get-go as hyperbolic, rather than circular functions like trig functions, there's a little bit of a difference to account for. Sometimes we get lucky, sometimes they exhibit the same patterns, but not every time. Okay, so, you know, what does the book ask you to do? What are typical problems going to look like? Here's one that reminds us of some old trig stuff where we wanted to prove the identity. So remember in trig, there were all these identities that we had to prove, and the way we did that was, you know, we are given a statement, and I'm just going to pick on this one, cosine hyperbolic of x minus sine hyperbolic of x is e to the negative x. So we're given a statement, and we have to show that this statement is true. And the way to do that is to work with one side, and I always like to say work with the sloppier side. In this case, maybe the left looks a little sloppier. It's not much I can do with this one term here. I would work with one side until I got the right-hand side. You never want to work both sides and meet in the middle somewhere, right? Because then you're like telling someone to read a book, first page, last page, second to last page, and you're telling them to read it, you know, from the covers into the middle. Nobody does that. So you're going to start from the beginning and work to the end, and then you'll show that the end is what is actually going to happen. So what I'm going to do is I'm going to rewrite the left-hand side just using the definition of these hyperbolic trig functions. So cosine hyperbolic, if I write it out, it's e to the x plus e to the negative x over 2. Sine hyperbolic, e to the x minus e to the negative x over 2. You can keep rewriting e to the negative x on the right-hand side every time. That's not like an abundance of things to write. Yeah, I say it. I will do it, right? Yeah. So I'm not touching the right, I'm just rewriting it. All right, these have a common denominator. Let's get them together. E to the x plus e to the negative x minus e to the x minus minus is a plus. Remember, you're subtracting everything in that numerator, not just the first term. So make sure you subtract that entire rational expression, i.e. distribute, distribute. And then the half's just sitting there. So we've got e to the x, but then we're subtracting e to the x. So those cancel each other out. I have e to the negative x. I add another e to the negative x. I now have 2 e to the negative x's over 2. And we're home free. All right, so we have shown exactly what they asked us to show. I just cleaned up the left-hand side based on the way these hyperbolic functions are defined, and a little algebra to get it to pop up e to the negative x. So when they say identities, they're not going to be anything crazy. It's 9 times out of 10, just rewrite these going back to the very standard definition of what those functions are in terms of the exponential function. And then some algebra steps, and you're done. And so there are some problems like that. Let's see what else we got. Find the limit as x goes to infinity, sine hyperbolic of x over e to the x. This will be nice because we probably haven't touched a limit in quite a while. So when I look at this, the sine hyperbolic function has this shape to it such that as x gets larger, the hyperbolic function gets larger and shoots off to infinity. And of course, same thing with the exponential function, right? As x gets larger, it shoots off to infinity. So right now, I would be looking at something like infinity over infinity, which is totally meaningless. That's not 1. That's not infinity. That's not 0. Right, so we can't make any sense of that. Instead, we have to algebraically sort of manipulate this. Now, it'd be very difficult to turn e to the x into some sort of function that would cancel out with sine hyperbolic of x. But it would be very easy to turn sine hyperbolic of x into its definition with e to the x and e to the negative x, and then play around with this e to the x. So basically what they're wanting you to do is write sine hyperbolic of x in terms of e to the x minus e to the negative x over 2. But then, of course, you still have the original denominator, e to the x. So that's what they're asking you to do. So you write that out, again, respecting the limit notation. If that notation is not here in the problem, your problem is meaningless. It has to be there. Otherwise, you lose the math. So the limit as x goes to infinity. Rather than dividing by e to the x with this rational expression, I'm going to multiply by the reciprocal of e to the x, which is 1 over e to the x. Now I can take this. This is 1/2 of all this stuff. I can pull that half out since it is just a scalar multiple. Right, we had that old rule that said if you had the limit as x goes to a of c times f of x, you could pull it out and say that that's the same thing as c times the limit x goes to a as f of x, because that multiple c is not affecting the limit other than just being a multiple of the result of that limit. So I'm allowed to pull that half out. There's all my numerator stuff, e to the x minus e to the negative x. I'm multiplying by 1 and then dividing all that by e to the x. So that's my denominator now, e to the x. So I have 1/2 the limit as x goes to infinity. Common denominator, so I'm going to write it like that, such that each piece is getting divided by e to the x. And you can see that this ratio is 1, right? E to the x over e to the x is 1. So I've got 1/2 the limit as x goes to infinity. 1 minus this e to the negative x really lives downstairs and is going to be multiplied with this e to the negative x. So this is e to the x squared, or e to the 2x if you like writing it that way. Now we finally just have this one piece that we can analyze and say, aha, as x gets large as it wants to, all the way up to infinity, then this is going to be e to some massive, massive power. This denominator is going to be huge. 1 divided by that huge number is going to go to 0. So I'm just emphasizing that this piece is going to go to 0. So I'm going to have 1/2 the limit as x goes to infinity of 1 minus 0. So you can see that this piece will disappear. That is just 1. So my limit is 1/2. Right, there's no way you could have told me that was 1/2 right off the bat. Right, so simply looking at this and saying, find this limit, and then writing 1/2, I would say you're crazy, and I'd like to know which internet search engine you found that from. And so it does take a little bit of rewriting, but when you do the rewriting, it's all just exponential function stuff. It's all just e to the x stuff. So a lot of nice cancellations and some easy algebra to work with in the end. Let's pick on something a little different here. How about a derivative? Let's say they give us find dy dt if y is equal to log sine hyperbolic of 2t. So just differentiating the sine hyperbolic function would be too boring. I already gave you all the standard ones. Let's throw some other functions in the mix. That way we know we're still making sure we're watching out for chain rule, product rule, quotient rule, all that good stuff. So be careful, this is a function of t instead of x. Right? No big deal though. What I want to notice is that I'm differentiating. The outer function is the log function, the natural log function. To differentiate the natural log function, I need the derivative of the inside over the inside. I'm going to write the bottom first because it is the inside. I need to do the derivative of the inside, but when I look at the inside, when I differentiate that, be careful, there's a multiple here, which means this is a function composed with another function. So I do need to use chain rule. So when I look at this, the derivative of the inside is going to be, well, the derivative of the sine hyperbolic function is cosine hyperbolic of 2t. There's the derivative of the inside with chain rule over the inside. And then if you really want to simplify this just a little bit more, I can rewrite this as cotangent hyperbolic. I'm going to put the 2 out front. I'm multiplying by 2, whether I do it front or back. Doesn't really matter too much. But I do need 2t, not just t in there. And that's it. Let me just emphasize what I did there. You wouldn't have to rewrite that. If you want to leave it in that ratio, that's totally fine. But you could rewrite it just so it takes up a little less space. In fact, like an answer in the back of the book would probably rewrite it to take up the least amount of space. All right, so make sure you're still obeying the properties for differentiating log functions, other trig functions, algebraic functions, of course, chain rule, product rule, quotient rule, all that good stuff. Let me see if I can grab one more. Yeah, here we go. Sine hyperbolic inverse. This one will go back to y prime if y is equal to sine hyperbolic inverse of tangent, we'll go back to x, just because it's, I don't know, easier to do. So we want to be careful here. We need to find our sine hyperbolic inverse derivative. Who cares about the inside right now? That is the outer function. So in order to differentiate that outer function, I need to find the derivative of sine hyperbolic inverse, which tells us to do 1 over the square root of 1 plus tangent squared of x, which means I've just differentiated the outer function with the inner function simply plugged in. And again, this notation means tangent x squared. So again, go back to the original sine hyperbolic inverse of x. All right, whatever this thing is in here gets squared in the derivative. Well, because I have something more going on, something more gets plugged in here to be squared. Now, I'm not even done yet. When I look at here, that's just differentiating the sine hyperbolic function with its pattern. But I have to use chain rule now because I just differentiated this function. All I did was copy and paste the inner function. Now I need to multiply by the derivative of the inner function, which is secant squared of x. The derivative of tangent of x is secant squared of x. So again, watch out for that chain rule. I differentiate the outer function with the inner function simply plugged in place. And then chain rule says, okay, now you have to find the derivative of the inner function and multiply by that. So I've done that. And again, in the back of a book, more simply put, that secant squared would probably be in the numerator, taking that placeholder 1 in the way there. And then it's just nicer to write it out with this notation. Rather than say tangent of x is being squared, they just say tangent squared of x. That notation means the same thing. It means tangent to x times tangent to x. Okay, so, as far as the whole section is concerned, it's just playing around with these newer functions. Again, don't spend time just blindly memorizing all these formulas and stuff that I gave you. But just practice manipulating some, based on some of these problems. The earlier ones are just using the functions, some identity stuff. The later ones are just some derivative stuff, so you get some practice with the derivatives as well. So just kind of work on those a little bit. And then, so exam 1's Monday, and what I'm going to do is make a separate video that kind of hones in on exam 2 a little bit better. I'm still making the exam, so I don't want to make the video before I make the exam and then change something. So once the exam's finished, I'll upload a video that sort of just hones in on, these are like more precisely the exact type of concepts that you're going to see, and this is exactly how I want you guys to work through your solutions. And then hopefully exam 2 should go a little bit more smoothly if I give you that little preamble ahead of time. So yeah, so look forward to that video. Otherwise, study, 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 and then exam, and then we will see you again for chapter 4, which is, chapter 4 is kind of, it's a lot more intense as far as the differentiating goes, but it's all just differentiate. It really is truly just, all of chapter 4 is just derivative, 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 some graphing, and then, just more derivative, derivative, derivative. So it really drives the point home. So thank you very much, and I'll see you for the review video and then in chapter 4.